And we've actually done some with leading coefficients, but the way we got around them is we like factored them out. Okay. Well, these aren't going to factor out like with a GCF, even though I might check it for that. They're not going to work. So let me give you a title here. So it's like trinomials with a leading coefficient. All right, so let's look at what I'm talking about here. Let me just jump into an example. So you got let's do 2x squared plus 5x plus 3. Okay, so let's see if you guys know what I'm talking about by a leading coefficient. What does that refer to here in this case? It's the 2. So it's the number that's in front with my x squared. So a lot of times when we first learn to factor trinomials, and what the trinomials we've been factoring, we've left off that leading coefficient. So none of them had that leading coefficient, and we didn't really have that problem. So if I'd look at this would just be like finding factors of 3 that add to give me 5, which wouldn't factor. Okay, but that's the way that we would look at that. Now, when we put that 2 in the front, it changes a lot of things. There are some similarities, but there's probably more differences in the way that I do this one. Now, before I show you the method that I'm actually going to work at here, the thing that we look at first, no matter if it's got a leading coefficient or not, whether it's a trinomial or not, should be what when I factor this? What do I always check for first? Yeah, GCF. Okay, so do I have a common factor here? No. Okay, so I can't factor anything out. Now, the next thing you need to check for is our new thing, is if it's a trinomial, is it a perfect square trinomial? So are these perfect squares? No, not even close. Okay, so it's GCF and then perfect square trinomials. Now we're going to look at it as a trinomial with a leading coefficient. Now we're going to use here, and if you want to YouTube this, because this is how I found out how to do this, it's called the Berry method. Okay, now I've taught something for 14 years called split and group on this kind of problem. And then I talked to a teacher that she teaches at West Washita. She's a dual enrollment teacher. And we were talking about factoring one day, and she said this, and I asked her, what's the Berry method? She tried to explain it to me like over the phone, and you can't really get it over the phone. So I YouTubed it, and I'm like, oh my gosh, this is the coolest thing ever, because I'm a dork. But anyway, when I watched this like in July, I could not wait to show my pre-calculus students this because it was just so much better than splitting and grouping. They did not share the same excitement, however. Now, they were like, oh yeah, okay, so it's just a different way. And I'm like, well, it's so cool. And yeah, okay, whatever. Now, so let me show you what the Berry method does. All right, so instead of factors of 3, what you look for are factors of, you take the leading coefficient and you multiply it by the last term. So 2 times 3 would be 6, okay? And what I do is always write a 6 over here and kind of circle it just so I can see it on the paper. It's not really going to come into the problem that much. So I'm not going to look for factors of 3 that add to be 5. I'm going to look for factors of 6 that add to be 5. Okay, so what are factors of 6 that add to be 5? 2 and 3. Okay. Now, let's look at some things that's not going to work here, but we'll change them to make them work. So 2 and 3. So you might think, okay, x and 2. Okay, x and 3. Because 2 times 3 is 6, and 3 plus 2 is 5. Now, here's the problem. Let's go ahead and put the signs in there, because that's the similarities. The sign rules are the same. This means that they're going to be the same, and then they'll both be positive. Okay. All right, so let's talk about some problems with this, about how this is wrong. Okay, so let's look. If I multiplied this out, if I said x times x would be x squared. It wouldn't be 2x squared. Okay, so we're going to modify it a little bit. And when we modify it, it's still going to be wrong, but this is where the Berry method comes in. So instead of putting an x and an x, I'm going to put a 2x and a 2x. And squeeze that leading coefficient in front of both of them. Now, that's not right either, is it? Okay, because 2x times 2x would be 4x squared. Okay, well, here's where it comes in, and this method is called borrow and payback. What we did is we borrowed a 2, and so now what we have to do is pay back that 2 out of one or both of those factors. Now, do you notice in the first set of factors there that it has a common factor of 2? So here's what you're going to do. And so the thing is, the Berry method, it always gives you something wrong, but you fix it. And the way that you fix it is you divide out any GCFs that you have right there. Okay, so it's like I borrowed a 2, now I have to pay back the 2. Okay, so now when I divide both of these by 2, what's that going to give me right there? Yeah, x plus 1, right? Now times 2x plus 3. Okay, so that's called the Berry method, or borrow and payback there. Now, do you guys want to see how I used to do this for 14 other years? No? Sure? Okay. Well, if you don't want to see, then close your eyes. All right. Now, yes, question? All right. Well, you got to do the inside and the outside. See, x times 3 would be 3x, right? And then 1 times 2x would be 2x. So 2x and 3x would give you 5x, okay? So that's one thing. That's a good point. I'm glad you said something, because you can FOIL it to check it, right? And so that's what we were doing, is FOILing to see how it was wrong and how when we made this modification right there, it turned out. Now, so let me show you what's called splitting and grouping. So this is what I used to teach before I learned this method. And it has some similarities in it. So you'd still multiply the two end terms to look for factors, and that would still be 6. So you'd say factors of 6 that add to be 5 are still 2 and 3. All right, but this one was called split and group. So what you would do is you would split the 5 into a 2x and a 3x. Okay, the factors of 6 that add to be 5 are 2 and 3. So you split the 5x into 2x and 3x. Now the sign rules still applied. They'd both be positive. And then you'd bring down the first and last terms. So what you're doing there is you're making it into 3 terms into 4 terms. So you're taking the middle term and making 2 terms out of it. Because think about it, what 2x plus 3x would be 5x, right? Okay. Now, after that, you take them and you group them. So that's where the term comes from, split and group. So you take the first 2 and group together, and the second 2 and group together, and out of the 2 groups, you would factor out the common factor in each group. Okay, so what's the common factor in that first group there? 2x. Okay, and then that would leave you with x plus 1. Okay, and then out of this group, I can get out of 3, it's actually a positive 3, so the x plus 1. Now, notice that you have another common factor. Both of them have a common factor of x plus 1. So you pull out another GCF, and the GCF there is x plus 1. So I take this x plus 1 and I pull it out. And when I pull out that common x plus 1, 2x plus 3 is left over. All right? Okay, that's called, look, got the same thing, right? That's called splitting and grouping. And it actually takes a long time. It takes a long time to split and group. Now look at the Berry method. Look how much simpler and shorter that is.
Okay, now you lost me. Okay, I see you working together.
All right, right here. Look, x plus 1, it's a common factor, right? It's the same. So I'm taking that x plus 1, and I'm factoring it out. Okay, so when I take the x plus 1 and factor it out, it's right there. Now what's left over? 2x plus 3. Okay, now, you're probably not going to see me do this. You might see me do this like if I post an old video from years ago or something, you might see me do it like this, but I'm going to stick with that Berry method. It's really it's shorter and it's less complicated, really. Okay, so it's both things there. Now let's do some more examples and let's try this. So now let's clarify. All right, when am I using this method right here? Not every when you have a leading coefficient. Now you're checking for GCF and perfect square trinomials first, okay? But yes. It's not that different. Okay, we're gonna see some. I'll do an example right now to show you that one. Okay. All right. All right. Yeah, both of the ends have to be perfect squares and positive, and then the middle one. Hang on, I'll show you in a minute. All right, let's try this one now. Okay. Let's do 3x squared minus 10x plus 8. All right, so let's see. Do I have a common factor? No. All right. Look at the ends. Are the ends perfect squares? No. Okay, now what was your question about the perfect square trinomial? Okay. All right. Now, let's look. Since there's no GCF, it's not a perfect square trinomial. Let's look for factors of something. Now, not factors of 8, though. Factors of what? 3 times 8, 24. Okay? So what are factors of 24 that add to be 10? Yeah, 6 and 4. Okay? Now, somebody earlier said 12 and 2. What's wrong with that logic there? They don't add, they would subtract. So if that would have been minus 8, 12 and 2 would have been correct. All right, but it's 6 and 4. Now, not x and 6 and x and 4, but 3x and 6, okay, and 3x and 4. All right, same old sign rules. What does that mean? Same, and they're both going to be negative. All right. So now, is that right? No. So the Berry method doesn't get it right. You have to fix it. Okay? So here's the thing. 3x times 3x would be 9x squared. So you borrowed a 3, so you have to pay back a 3. Where can I get a 3 out? Right. This first one, it'll come out of there, won't it? All right, so you divide this by 3, and now it's going to be right. All right, so this would be x minus 2, all right, times 3x minus 4. It's shorter and it's easier, okay? All right, let me show you one that's kind of like that, all right, where, you know, we borrowed a 3, so we paid back a 3. We're going to see one where you don't really get the whole number back, okay? All right, let's try this one. Let's do 15x squared minus 19x plus 6. Okay, now, let's check. GCF. No. If this would have been, 21 or 18, okay, you could have factored out a 3. Well, we got to check for a GCF and a perfect square trinomial first. Okay. Now, so there's no GCF. Now, is it a perfect square trinomial? No. All right, so now let's go to the Berry method because I got a leading coefficient. So it's not factors of 6, but factors of 15 times 6, which is 90. Okay, these might be a little bit hard to find. So what are factors of 90 that add to be 19? Yeah, 10 and 9. Okay, it wasn't that bad. Now remember, if you can't find factors of the numbers, you can always list them. Make a list until you find them. All right. Now we said 10 and 9. So not x and 10 and x and 9, but what do we have to throw in front of the x? 15. So 15x and 10 and 15x and 9. Okay. All right. Signs are going to be same and both negative. Okay. Now, Now watch what happens here. This turns out pretty cool. This isn't right, is it? Because 15x times 15x would be 225x squared. Okay? Yeah, very good. You're going to have to, do you notice that you could get a common factor out of both of them? Okay? So a 15 doesn't come out of this, but a 5 does, doesn't it? Okay, so we'll divide that one by 5. And what will come out of this one? A 3. Now do you see where the 15 is? 5 times 3. There's the 15. So sometimes you have to pay it back out of both of them. Okay? And a lot of times when that happens, it's because this one and this one have a common factor. Does that make sense? 15 and 6 have a common factor. And these don't have any common factors, then you end up just paying it back out of one of the factors instead of both. All right, so now, here we go. We paid back 15. Let's see what it's going to give us here. This would be 3x minus 2, and then 5x minus 3. Okay. All right, let's look. All right, I'm going to do like 2 more examples with you, okay? Let's try this one. Let's see, 2x squared plus 6x minus 8. Okay, 16, and then no. GCF of 2. All right, I got your condition to look for. So now, we can factor out a 2. Now, one thing about the Berry method where, splitting and grouping, if you didn't factor out the common factor, you could eventually fix it. You can't fix it in the Berry method. If you have a GCF, you have to factor it out. If you don't, then the problem's not going to work. Okay? Now, let's factor out a 2. So we get 2 times, it'll be like, what, x squared plus 3x minus 4. Now, let's look at this. What's left? All right. Is it a perfect square trinomial? That's negative. Okay. Even if it was positive, it wasn't going to be 1 because this would have been x, this one would have been 2, and 2x doubled would be 4x, not 3x. Okay, but it was close. Now, notice something. Once I factored out the 2, do I have a leading coefficient anymore? No. So, do I need the Berry method to do this? No. Don't need the Berry method because it doesn't have a leading coefficient. So it's just factors of 4 that subtract to be 3 are 4 and 1. Factors of 4 that subtract to be 3 would be 4 and 1. So x and 4, x and 1. Yes, signs are different this time. So we do plus 4 and then minus 1. Okay. Now, before I do the next one, I'm going to tell you a story, but I'm going to pause this. A little random story. All right, here we go. Last one, and then I'm going to let you guys practice on this. All right. So now, you tell me through this one, okay? GCF of 3. So if I start saying 6 times 21 and looking for factors, I'm going to miss that because you have to get the GCF out first. So I would get 3 times, now we'd have left 2y squared plus 9y plus 7. Okay, now look at what's left. Is what's left a perfect square trinomial? No. Okay, now with what's left, do I need the Berry method to factor what's left here? Yes, because it's got a leading coefficient. Okay, so sometimes you get the leading coefficient out, like here, and you don't have to use the Berry method. But sometimes what you do is you have a leading coefficient left, and you do. So it's not factors of 7 that I'm looking for to give me 9. I'm looking for factors of 14. Okay, so factors of 14 that add to be 9 would be 7 and 2. Okay, So now we're not y and 7 and y and 2, but 2y and 7 and 2y and 2. Okay, the signs are, and both of them will be positive. Okay. All right. So now if we use the Berry method, we always have to fix it. So we borrowed a 2, so we have to pay back a 2. Y'all see where the 2 is going to come out of the second one this time? A lot of the times it comes out of the first factor. Sometimes it comes out the second. All right. So this would leave me with 2y plus 7. And then this would be y plus 1. Anybody? All right. The 3, that's Uncle Wes. No, I forgot him, so I got to turn around and come back and get him. There you go. Okay. All right. Because when you use the Berry method, look right here. 2y times 2y will give you 4y squared. Okay. So every time you use the Berry method, you have to divide out any common factors to pay back the 2. Okay. So the Berry method, the ones where you have the leading coefficient, you're always going to have to divide at least one number out of one factor. Remember that one we got 2 of them, and sometimes 2 of them. All right. Now, y'all look at the sheets that I gave you yesterday, those factoring worksheets. Okay. They have 4 sets on them. They're numbered like 1, circled a 1 on the first one is GCF, 2 on trinomials without a leading coefficient. All right, on the back of the first page is set 4, and that's what you're going to be working on. So set 4, you're going to do the third column. So there's 1 and 2. There's 3 and 4. One of these days we're going to come back and do set 3. Okay. All right. So you got set 4 there. The third column. Now you can't see the last problem, so don't worry about it. Now the last page, you have the answers for you there. Okay, so you can check them. All right.